superconductors in a also brief way. And then the most important thing is the concept of entanglement of topological systems. I think there are two different topics, but they can also be very much related and also have been studied very intensively in these 10 years. So then I talk about how we do from this spectrum of entanglement to feed the machine and get some result. That's my part. And deep learning just, I think, come because the NVIDIA GPU get the ImageNet champion, and also because GPU is very fast. Actually, the algorithm has been developed for almost 50 years. So, but recently it came to in a very fast way because GPU speed is very fast. So, therefore, the first is come to the machine learning. Machine learning actually you have to define the function and evaluate search, and then you pick the best function. So you have this function, and the simple function is the step function, and then you go to this kind of other line function or other different functions, and then you have at the end this softmax, or you have this remove function. But the function you pick and you can help you choose the best result, then that's the best function. So, but for the machine learning, there are four different ways. I mean, there's different ways. And the first way is supervised learning, and then or unsupervised learning. For supervised learning, you just give the machine the idea which kind of things you want to tell. Like if you want to have orange or apple, you just feed them orange picture and apple picture, and then supervise that. But in another thing is unsupervised is that you feed the data, and then the machine can give you a cut line, and this cut line will tell you the difference of these two different data, and then it's unsupervised. But it's also semi-supervised learning that you just give kind of half of the supervised data, and then the other you don't give, and then you give you some result. And then or enforcement learning that, like if you want to fix the data in the time sequence, then you can put the time sequence data and always have feedback to the machine, and then they will learn from the time sequence. So this is reinforcement learning. And they use these artificial neurons. Actually, artificial neurons is like this. So this is actually actual neuron, but actual neuron you have the input, and then you have kind of feedback, and then you have this output. So therefore, you have input, but then you have a feedback into this input, and then you'll get output. And this is kind of idea of machine learning or deep learning, that you have this neural network, and then you have different main model architects. Like CNN is like you feed the 1D data, and then you just get different layers, and then you just get output from different activate functions. Or you can also, like for the image, the best way is CNN. This is also 2012 that this NVIDIA get the champion because they use this CNN skill, and the CNN skill will scan the big picture in a way that they use kind of, we call maybe the truncated basis and into different layers, and then you just go through these layers and then just get output. Or you can also do the recurrent neural network, RNN. Actually, RNN is like if you have some data that have time sequence. For example, if you have the data, movie data, or you have this kind of speak data, then each voice speak out with different time. So then you have to distinguish, and you have to have feedback like this. Then this is a time sequence. You put the time here input, and then you correct that and put another input, and at the end you have this. And this is RNN. But for us, the first two are the useful tool in the physics, because normally we don't have this time sequence. So then you have this difference. This is CNN structure. Actually, you have this picture, and then you have for valid padding, you just have different layers. You create like different layers, and different layers can help you to see different features. Like in this one, you can see one feature, and different layer have a different feature. And then you can do the max pooling that you just reduce the amount of information by like truncation. You have to have the most important message, and then you just put that into a small amount. Then you get another padding, and you just flatten that data to the 1D, and at the end you get this output neural network. So this is CNN structure, and we will intensively use this one because in our study, actually we get very much like the image. So the image will really tell you the phase transition points. So therefore, this will be used. But also, this DNN will be also used because we also create that one-dimensional data. For example, it's the eigen spectra of this entanglement matrix. So therefore, this eigen vector, where eigen values can also be used in this kind of DNN structure. So the next topic I want to talk is to give you some idea, but I think most of you also know that this topological system in 2016, three gentlemen got the Nobel Prize actually for the discovery of topological phase transition. The main doer is Saulus and Totelis, and then the topological phase emitter is these two gentlemen. So our talks actually very intensively related to this discovery. What is topology? I don't think I have to talk much about, but it's like just this doesn't have different topologies. It's come from the Euler topological number, and then we'll have something to do with these holes, and then like this coffee cup. If you reform that, and then you still have the same shape as the donut. So this coffee cup has the same topology, as we can say. Therefore, for us, in these 10 years, we very much intensively want to discover one of the signature of the topological stuff. This is the Majorana fermion. Actually, this Majorana fermion comes from the P-wave superconductor. If you have P-wave things, then you can separate that to like two different half fermion, and these two different half fermion, one half of that will connect to the other half of that, and the end it leads to like half fermion here, and then you have this Majorana fermion actually is characterized like half electron, half fermion. So then they have this half fermion property, and this is topological. That means that it won't be influenced much by the noises. And then how to do that? Actually, these 10 years also, or this already 12 years, there's a method that you just put a semiconductor wire with very strong spin-orbit coupling, and this spin-orbit coupling on the S-wave superconductor, then it will produce kind of a proximity effect, and this proximity effect will produce kind of artificial P-wave chain, and then you can really observe the Majorana fermion here. This is STM scan by the Princeton group, so you really see very strong signal here. So therefore, for the superconductor, we need to use, actually, you have different feature, but I don't think I need to show that. Why I want to show this? Because what is the topology? What is the topological matters? Actually, it's very interesting because in the normal, like ferromagnetic stuff, you have this magnetism or antiferromagnetic, you have antiferromagnetic ordering. Or in the superfluids, you have superfluid density. Or superconductor also, you have also this kind of superfluid, so you have also the super fluid density, and then you have this order parameter, and then you can use Ginsburg-Laudau, and Ginsburg-Laudau actually based on the spontaneous symmetry breaking. If you have spontaneous symmetry breaking, then you can have Ginsburg-Laudau, and then Ginsburg-Laudau, you have this order parameter, but you have Ginsburg-Laudau, and then you can find that in which temperature the system will go without ordering. And inside the critical temperature, the system has ordering, and then you have the phase transition. But this kind of phase transition, actually, you need to have spontaneous symmetry breaking. So like you have something point up. If you have this kind of a spontaneous symmetry breaking, then you can form the order parameter. But we have Mermin's Wagner theory that tell you that in the low temperature, it's not very easy to form the symmetry breaking. So actually, for the finite temperature, 2 dimension already cannot give you the symmetry breaking. So therefore, for the low temperature, like for 1D, and you don't have this kind of symmetry breaking. So we don't have this, but topological system, actually, you don't need a real symmetry breaking. For example, for this Tholos and Tostalis, they found these 2D XY models, and they have written down these 2-dimensional finite temperature models that cannot have any symmetry breaking, but they have phase transition here, and the reason is that they have this kind of vortex anti-vortex pairing, and then this don't break symmetry, but they have this kind of disorder here, and then for the higher temperature, you have like single vortex here. Therefore, they have they don't have symmetry breaking, but they still have this kind of critical temperature, and this is without symmetry breaking. We don't have order parameter. But we still can have this kind of phase transition, and we call this topological phase transition. So therefore, for this P wave also, we have this topological superconductor. Actually, I have to show, I think this is repeated. So then we can write down actually discrete models if you have kind of a lot of amount of that, and you only study the low temperature feature. So you can also use this discrete model to describe that. Or you can make that, this is a Dasama scheme that you make quantum dots and superconductor, use the proximity of phase between these two, and use skateboarding to control the chemical potential, and then you have this gap formed by this proximity effect, and then still can form the 1D pure superconductor. So you can use these two different. Then this 1D pure superconductor actually really have phase transition, but they don't have symmetry breaking. So they are topological phase transition. So how to characterize the topological phase? Actually, you can use different scale. One scale is Berry phase, that you just in the parameter space you just move the parameter in adiabatic way, and then if you go back to the original point, then it will accumulate except this time evolution of energy, but also Berry phase. And this Berry phase will be non-trivial. That means there will be pi or minus pi in the topological phase, but in the it will be 0 in the trivial phase. And this is the Berry phase. Or if you do that in the momentum space, or then you have the Z phase or wave vector phase. So therefore, Berry phase actually can give you some idea if the system in the topological state or not. This is the P wave. We have the P wave model here. We have here the coupling between these two like spinless electron and then you have superconductor gap, but the superconductor gap is not between K and minus K, but between I plus 1. Therefore, they have like neighbors, the superconductor gap, and then this will form your P wave structure, and then you have chemical potential, and then you have this parameter, and then you just can see that it's a phase transition, and if you can adjust the delta, but you will see how large delta is, the system will have the same structural phase transition, so they can be shifted in a way. So mu actually, if you between 2t and minus 2t, and these two are topological phase, and these are non-topological phase in trivial phase, and that is you can calculate the Berry phase and can use very easy argument to characterize this by the Berry phase is pi inside this two. You can calculate that. Or outside, and you will get zero Berry phase. Therefore, we have this phase transition, and this is topological. That means you don't have symmetry breaking, so you don't have all the parameters, but still can have this phase transition. And that will be somehow that will have some problem because if you have topological phase transition, you don't have all the parameters. If you want to do some machine learning, what is the data you can feed because you don't have all the parameters. So we really have this trouble to feed that. If you have like easy model, you can feed the magnetism to the system. But if you have topological system, you don't have all the parameters. You don't have anything to feed. So that's also our question in the beginning. Actually, we also did the critical behavior of like easy models. Then we get some interesting results, and then we ask our question how to characterize the topological system. So this is the classification. I don't think I need to show that. So therefore, we think about entanglement because entanglement is actually a very interesting thing. And for this kind of simple quadratic model, because you don't have interaction between like electrons, therefore it is the entanglement you can really calculate it in a very simple way. I will tell you how. So I don't need to. So I think I prepared it for the students, so it's easier to. So this also in entanglement measurement is also but I think a lot of quantum people don't know why entanglement entropy actually become one of a measurement, but I think I also skipped that. Sorry. So one of the measurement is entanglement entropy. Entanglement entropy can be calculated if you have this quadratic model, and that also was a long study. When I was a very young PhD student, we have this question how to calculate entanglement spectra, and actually that time we didn't know the entanglement spectra. We almost only know we have DMRG, and then what is the situation that DMRG work or doesn't work. And in that situation, we have to calculate like a spectrum of a reduced density matrix. Reduced density matrix is that you integrate out the environment, you get some of this reduced density matrix. But the outcome is this reduced density matrix is actually the tool to calculate the entanglement spectra. Okay, and then you have reduced density matrix. You just trace out your environment. You have two parts of system. One part is your this is whole system, and then you cut one part. And this part is the system you want to consider. Another you consider another is environment, and then you just integrate out the environment, and then you get the reduced density matrix. Then you have to calculate the von Neumann entropy here. This von Neumann entropy will tell you the entanglement between these two. What is the theory that is by OPES in 1996? Actually, OPES, they did that in a way they do this entanglement formation, and the entanglement formation, actually, you really have this entanglement entropy calculated the way I told you. And the meaning is that you have this n copy of phi AB, and then you can through the local operation and classical computation, get n copy of maximum entangled state. And actually, you just transform the system into n copy of maximum entangled state. Therefore, this divided by this will be their entanglement. So this is a very strict proof that entanglement entropy will be defined in these ways. Actually, the real measurement between two systems. Okay. So therefore, for us, it's very good because the only thing we have to calculate is this entanglement spectra. And this entanglement spectra, we use the coherent state to integrate out the group, and we use coherent state to integrate out that. And then you can, by diagonalizing the block green function matrix or correlation function matrix, and then we found that different group found that by using different scale, but lead to the same result that you just diagonalize the correlation function matrix, you get the lambda m, and you get the entanglement entropy. But for us now, entanglement entropy is no longer very interesting. Actually, entanglement entropy was interesting because if you don't have machine, and then you can look at the structure, and in the critical point, the entanglement entropy will diverge for the second order phase transition. So therefore, entanglement entropy was very interesting in 2000 to 2010. I think people really studied that. But for us, entanglement entropy is no longer very interesting because we found entanglement spectra here is much more interesting. They have a very rich structure here. Another very interesting is entanglement eigenvector. Actually, eigenvectors, you diagonalize this reduced standard matrix, and you get the eigenvector of that. Then that value is also very interesting because you can really see the H state of a topological system. And that was something very interesting. I'll give you an example how to calculate this kind of correlation function matrix or green function matrix. Handy code is green function matrix. Page code is correlation function matrix. So I will use these two in the same time. So then you just have to separate two different systems, and then you can prove that if you calculate only the correlation between between different sides and to form a matrix only inside the system A, then you can diagonalize that, you can get eigenvalue, and this eigenvalue actually give you one particle entanglement spectra. Then you just sum up then, and you get really the entropy. So in a way, so you can calculate this one. But another thing is entanglement spectra. Actually, entanglement spectra has been studied for a very long time. In 1988, they have already studied like entanglement spectra, or the spectra of this reduced density matrix using a corner transform matrix. This is by Page and Neurons. And then they found that it have some very interesting structure, and it can really do something. But then I think they will become popular because one very famous guy, Hoden, and his student Lee, they did this kind of interactive entanglement entropy. And they found that for the entanglement spectra for the low temperature top will mimic, if you have a conformal field theory, and this part will mimic the conformal field theory. So therefore, entanglement spectra somehow become very important in the strong correlated system. This is more risky. This is like non-abelian fractional quantum Hall state. Then it found out this idea, and people begin to be very interested in entanglement spectra. But actually, I have to address that entanglement spectra actually have been studied for many years, even to 2008, already 20 years. So even I think earlier the quantum chemistry people, they are very interested in the reduced energy matrix because they know that reduced energy matrix can give you a lot of information about the system. And then they already use kind of things, but they just didn't call it name. Okay. So then for us, then this can be actually done, and analytically you can calculate the Bloch correlation quantum matrix for kind of a P-wave superconductor, and you just use Nambu notation. They have C and C dagger, or CK and C minus K dagger, and then you just stabilize that in a way. So then you can also form this Bloch correlation quantum matrix. And then interesting things that you can go to their K-space, and you can find this structure. And we also use this structure actually in our calculation. It's very easy to do this in a calculation. So you just have to form an Nambu basis, and then you just diagonalize. You just do the Fourier transform, and you get this. And look at this form. This has R dot sigma form, and this R dot sigma is eventually very similar to the R dot sigma in the original. Sorry. If you look at the system here, and this R is because you form a Nambu notation, so you form this R dot sigma because sigma is SU2, so you can form any SU2 matrix to form like a Hermitian matrix here. So therefore, you have this R dot sigma in the Hamptonian. You have this R dot sigma in the Hamptonian, and then in the entanglement spectra there, you also have this R dot sigma. This is very interesting to explain why you have also the same structure in the entanglement spectrum as in the low energy spectrum. So, or zero energy spectrum. So therefore, you have R dot sigma here. So the condition for the Hamptonian that you have H state, you have topological system, is that is also guilt for this entanglement spectrum. But remember, you have this 1/2 here. Therefore, if you have the zero energy here, because R dot sigma will give you inner energy, you have the finite chain of the P wave, and that is characterize the topological system because the Marwana fermion is there. Therefore, you have 1/2 here for the Bloch wave function matrix. This characterizes the signature of the entanglement spectrum for the topological system. Okay, and this will give you, if you consider the eigenvector of this 1/2, you really see the two very sharp edge on the edge of the block you cut. So therefore, this is also a signature. But we don't tell machine that. We don't tell machine they will have these two peaks. We just want machine to know, to characterize themselves. And they really do. And very amazingly, they really found the phase landing point according to this structure. So that is their trends of machine learning. This also surprises us very much. So you have your energy state here, then you have the maximum entangled state here, and that is a one-to-one correspondence. These two are different systems. This system is the system you have a finite chain, and this system you have an infinite chain. You just cut them and to calculate the entanglement between these two. But the outcome is the same. Okay, there's something like these are two measurements for the topological system. One measurement is that you have a one chain. You just cut them, and you find they grow H state. Another is that you have an infinite system, you measure the entanglement between these two, and you measure the entanglement spectra, you get 1/2, and you measure the entanglement eigenvector, you get the H state. That's two different concepts, but they are one-to-one correspondent. So therefore, we back to the 1D P-wave superconductor, we found that in this phase, you don't have H state. they behave like a normal fermion. The two half fermion, they just glue together, and then they don't glue to the other. They don't, they are very, 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 faithful. They don't cheat. Okay. But for the topological system, they cheat with neighbors. Okay. They just connect to the neighbors, and then they leave their, husband and wife alone at home. So they just have this single pair. Okay. So, okay, well, I have only 5 minutes. So, how to fit deep learning process? We can form this kind of correlation function matrix, but for us, we need something like pictures. Therefore, if you form this group function or correlation function matrix, we get that complex number. We want to avoid that. Therefore, we calculate actually a Majorana correlation function. It's between two Majorana fermions, the neighbors. So you have to form these Majorana correlation functions and blockly. So you have block. Or you can also fit the one particle entanglement spectra, as I said, I told you. Another thing is the eigenvalue of block correlation function matrix is that eigenvectors. You get the entanglement eigenvectors. I told you it's the eigenvectors of a reduced density matrix you form. So you can fit these three. And this is the picture we just characterized with colors of the Majorana correlation function. Actually, the 2 and minus 2, this is 2. Okay, 2 is the or minus 2. These two are the age. So the phase boundary 2 and minus 2. You see, this is the kind of trivial state, and this is kind of topological state. But you don't really see much with eyes, right? You don't see much. You just see different colors. They don't have spatial form. Okay, but then you feed that to a machine, and we use this CNN structure. We don't do the pudding because information is very, very small. So because we use 5 times 5, 20 times 20, still only have 400 blocks. So therefore, we don't do the mass pooling. We just have padding. So we have this 20, 20, 46 and 128, and then we just enlarge that to 1 dimension and do this sort max. Then we get this result. This result is actually, you find that for the small, like L equal to 20, you get this kind of shape. And this probability of phase 4, and this is probability of phase 1, and this probability of phase phase 3. And then you see a phase 1 and phase 4 will have this phase boundary, but they are not 100% recognized. Then we found that they have finite size effect. If you see the L equal to 5 and 10 and 20, they will go sharper and sharper. But if you count the point here, this is 2 minus 2.01, and you get like error 0.01. It's already very small. So they really recognize different phases here and here. And then we get loss is like 10 to the minus 6. So after 15 of epochs. So therefore, this is very good loss. It's very consistent to this result. And that is the other training we train from here to here. But we just see the phase. I just characterize this is the phase 1, and with the point here is their point. And then I draw this phase boundary, and this phase boundary will give you here, this is also a phase boundary here, it will give you 0.004. It's also very small. So you really get very small from 1 to 3 phases. This is also amazing, very good training. Actually, it's very interesting. Even you do very small size, actually we do no small size, but if with this kind of closing, you really can characterize the phase energy in a very precise digit. So that also surprised us. That means the Majorana correlation function matrix is really very good to characterize this kind of phase transition. Another thing is we want to use one particle entanglement spectrum, and then we found that it's good also. But the things that it can only characterize phase, topological phase. But for the trivial phase, they have like 50% here and 15% here. That means for the one-dimensional entanglement spectra, one particle entanglement spectra, they cannot recognize different phase, different trivial phase. They can only characterize the topological phase and the trivial phase. But for the trivial phase itself, they don't have any idea. They will say, oh, it's the same. But it's also very reasonable because for this kind of entanglement spectra, your structure inside topological phase and inside the trivial phase are very similar. You have this one-half structure, you don't have this one-half structure. They look like similar. So therefore, they just don't know how to characterize the different phase. We can say we cannot, tell the different matter with different gauge, or U1 gauge here. But if you do these eigenvectors, you see the eigenvector spectra, each eigenvector each eigenvector is here. And then you see between 2 and -2, this is 2 and -2, this is but inside, you really see they have H state here and here. You see, this is very blank. That means the H state here and here can be characterized by the eigenvectors. So, therefore, for eigenvector is also very interesting. But we just do that, and we found if we only use 2 eigenvectors, the sharp edge can be found. So, and they can distinguish different matter of different gauge. Like this is a trivial phase, and this is another trivial phase. The green and orange, they won't mix together like 50% here. They are different. But the topological phase is also very clear. If you only use 2 eigenvectors, and these 2 eigenvectors actually have this H structure. But unfortunately, if you use more eigenvector, like whole eigenvector, then they will somehow have very chaotic structure here. And then the reason I think is if you have a picture, a very big picture, and then if you the only characterized things is this eigenvector of ages. So you have ages. But the other thing, they look similar. They are all box states. If they are all box states, they look similar, and then the machine are confused, and they cannot really find this difference. So therefore, they have this kind of misunderstanding, and that maybe we are not good enough. We are looking for a way to solve that. But in a way, we are doing that. We have these things. Okay. So, this is my conclusion. I think you can read that by yourself. So, thank you for your attention. Okay, question.
More questions? Okay. Okay, so here you're feeding it the entanglement entropy, entanglement spectra into this, and that works. So I'm curious, have you tried doing the naive thing of just feeding it more conventional, non-topological quantities, and seeing if the machine learning can identify the phase transitions? I kind of assume it can't, but.
For example, which kind of quantities? Variables, but variables is very easy. If you have only one value, if you will calculate that value, is like in entanglement entropy is only one value, and then you can really see the sharp things. Actually, machine can do that, and you will feed that entanglement entropy inside, but it's boring, right? It's also a function of function that really get diverged. And then they say, oh, it's diverged. It's like people, like person, human being see that peak and say it's phase transition.
So I guess for this system, I don't know the relevant synthetic observable. So people have tried doing this with the KT transition in the XY model.
Yeah.
And they tried feeding it I think this is Snellcow at Ginsburg, but they tried feeding it just here are the spin, here's the spin configuration, and it turns out that it can't learn that, this like kind of stranger observable, right? Like,
I think the string structure is actually, they can learn that. I think so. I think they can see the pattern more.
I think they had to tell it, like, they had to give it vortices, like, they had to give it, like, the vortex number or something like that. They couldn't just give it directly.
Okay.
Anyways, like, this is interesting because that's, I think, the thing that's hard is, like, finding these phase transitions that are not just the Ising model. And so it's maybe a good way to access that.
Thanks. Any more questions?
Thank you. I think it's very interesting because it can distinguish trivial and non-trivial, and even the trivial phase it can distinguish again. So do you try it to some conventional phase like symmetry broken phase? So
Yeah, actually we try also similar way we try, but it's also kind of cheating. We try the transversal Ising model. And from transversal Ising model, you have conventional symmetry breaking, right? But then we also have to, okay, we can also form kind of this matrix. But this matrix is very more complicated because if you use conventional local spin operators, and then you need more and more like a matrix. But you transform that to this kind of fermion using Euler-Wilson transformation, and then you can really also do the same trick. And then you characterize these two. But if you transform that to using Euler-Wilson transformation, actually you transform that to one branch of the P wave. Okay, so we have this kind of tree, and that will map the H state. If you do the local transformation to this H state here, it will transform back. If you transform back to the spin model, it will transform back actually to the symmetry breaking state. Okay, this kind of so we try actually. Okay. We want to try more. We want to try, for example, bosonic model, because we can also write on the same bosonic system. And bosonic system is also have very similar structure and have very similar things to do. So therefore, I think, for example, for this bosonic like Hubble models or like bosonic things, we also can do the same trick using this method.
I have a question. So basically, you use the entanglement spectrum eigenvectors to determine the phase transition, but it has been known that it is possible to define phase transition from this information already.
I know we want to.
Why should you repeat it, right?
No, but actually, if you do give machine that information, machine don't know what is that. You have to think as machine, not think as human being. Okay. Why we want to do that? Because when you can stand that, you remember you can do the experiment for some systems. Experiments can give you kind of correlation function.
But not,
and if you
know entanglement spectrum.
Yeah, you can design this kind of thing. You don't need entanglement spectrum. It's a spectrum of like correlation only. That we feed that. We don't feed entanglement spectrum. So you can, like, you have the very small system like 5 times 5, and then you can do the experiment with these 5 times 5 features, and then you just produce these features and feed that to the machine, and then will tell you if you have phase transition or not. Okay. Even we also did this is a supervised version. Okay. We also did a non-supervised version. They can only give you very clear difference between the two states, and they can also find the phase transition. I didn't put that in the slides, so because we didn't publish that result. So I think it's interesting. Actually, theoretically or experimentally. Okay, you can. I tell you the image is even 5 times 5. You have a very small matrix. You have to form this pattern, and then you just give a machine that can tell you something. And we also try 2-dimensional things. It's also very, very, very beautiful. So I think it's kind of ideal tool for topological system. This is only a try. We will try another system.
Okay, thank you. Questions? Okay. So if no questions, let's thank Professor Zhong. So we are going to have a lunch break. So we should have a lunch break outside for 1.5 hours. So the afternoon session starting from 1:20. Okay. So welcome back.
因为它要2分之2有分4分之1。对啊，对啊。只要